Students, this experiment is intended to determine the force induced on a vein due to impact of jet. The experimental setup is shown in this photograph. A pump is used to supply water, and at the end of the pump, at the end of the delivery pipeline, there is a nozzle fitted, and from the nozzle a jet of water is issued as shown in this figure, and a curved vein is attached to the lever. This is the lever onto which a curved vein is attached as shown in this figure. This lever is supported using a hinge at this point. On the other end, we have got a counterweight, and apart from the curved vein attached to the lever, a pan for adding the dead weight is also attached to the lever at the other end. When the jet of water is issued from the nozzle, the water will be hitting over the vein, and a force will be acting on the vein. This force we want to find out experimentally and theoretically. So this is the another view of the setup. The nozzle, from the nozzle the jet of water is issued. This photograph shows a use of a curved vein which is fitted onto the lever, and the jet after hitting over the vein is coming out at an angle. So these are the various elements of the setup. The hinge point is shown here. The lever is hinged about this point, and this is the lever, and this is the vein, and this is the pan over which we can be able to add the dead weight. The schematic sketch of the arrangement is shown in this figure. The entire lever is hinged at this point, which means that the lever can be rotated about this hinge point, and one end of the lever is attached with a counterweight. The counterweight can be rotated to change the position of the counterweight, and the vein is here is curved vein. Now it is shown fitted here. It can be replaced with a flat vein also, and the other end of the lever is having arrangement for adding weight, dead weight, as shown in this figure. So before starting the experiment, before issuing the jet of water from the nozzle, the lever has to be balanced. What it means is we have to adjust the counterweight until the lever becomes horizontal. Once it becomes horizontal, then we can start the experiment by adding a dead weight of known amount on the pan. So when you add a dead weight of known amount on the pan, the lever becomes unbalanced. So the lever is rotated towards clockwise direction due to the weight acting on the end of the lever. So these are the various measurements. The curved vein is fitted at a distance of L2 from the hinge point, and the dead weight is hanging at a distance of L1 from the hinge point. This figure shows the nozzle. From the nozzle the jet is issuing, and it is hitting over the vein, and after hitting over the vein the jet is coming out at an angle. We have to find out the actual force experimentally. FA is the actual force. We have to find out experimentally. Now, once a weight is placed over the pan, the lever becomes unbalanced. As a result, the lever is rotated towards clockwise direction. To make it balanced, we have to allow water to be hitting over the vein by rotating the valve. The valve has to be adjusted until the lever becomes balanced. So we have to open the valve until the lever becomes balanced again. So in that position, in the balanced position, the momentum created by the dead weight becomes equal to the momentum created by the actual force Fa. So that is what is written here. When the lever is balanced by adjusting the gate wall, the momentum due to Fa is equal to momentum due to dead weight W. So the momentum due to Fa is found. So momentum is the product of force into distance. So force is the Fa, distance is the L2. So this is the momentum created by Fa. And what is the momentum created by the dead weight? So dead weight is having a force W and distance is L1. So Fa into L2 is equal to W into L1. So here unknown is Fa, actual force Fa we have to find out. We can use this formula. So W into L1 divided by L2. So where W is the amount of weight placed on the pan, we have to substitute in Newton. So in case of a curved vane, after hitting the vane, the jet comes out at an angle. So this angle is 25 degree for the experimental setup used in the laboratory, and we have to find the theoretical force. Once we find the actual force Fa, the same force acting on the vane can be found out theoretically also. So using the formula what is given here. So the theoretical force Ft is given by rate of change of momentum, which is given by mass flow rate m dot into V minus of minus V cos alpha. Since after hitting the vane, the velocity direction is changing. So that is the reason why you have put a minus sign in this formula. Okay. So and this cos alpha is nothing but the angle at which the jet comes out after hitting the vane. So the mass flow rate can be found out using rho into Q. Q is the discharge, and the V minus of minus V becomes V plus V cos alpha, and V can be taken outside, and rho QV into 1 plus cos alpha is the formula to be used to find the theoretical force acting on a curved symmetrical way. So we need to find out the discharge Q and the V velocity of jet of water to substitute in this formula. So the discharge can be found out using the Culting tank method. So the jet of water after hitting over the vane is getting collected in the Culting tank. So this is the Culting tank. We can find out the time taken for or centimeter of rise of water level in the Culting tank. So with the help of that data, the discharge can be found out. So AR by T. So R is the rise of water level in the Culting tank, T is the time taken for or centimeter rise of water level, and A is the area of cross section of the Culting tank. So once you know the Q value, we can be able to find out the velocity at which the jet is issuing from the nozzle. So the nozzle is having an area A. If you know the diameter of the opening of the nozzle, we can find out the area using the formula pi d squared by 4. So if you know the area of the nozzle, we can find the velocity from the discharge. So velocity is given by Q by area. So Q divided by pi d squared by 4, where d is the diameter of the nozzle. So once we know the value of Q and d, we can substitute in this formula to find out the theoretical force acting on the vane. If the curved vane is replaced with a flat vane, the formula to be used is shown here. So F theoretical, Ft is given by m dot into V minus 0. So why the 0 comes into picture here is, after hitting the vane, the water diverts by 90 degree. So we have to find the component of this velocity along this vertical direction. So the component of this velocity along the vertical direction is 0. So that is the reason why it becomes 0. So mass flow rate can be found out as usual, rho into Q into V can be found out once the Q is known. After finding the theoretical force and actual force, a graph can be drawn between the discharge and the force. So the two graphs can be drawn on the same, taking the discharge on x-axis, force on the y-axis, and the percentage deviation in the theoretical force can be found out using this formula Ft minus Fa by Fa into 100. And one more graph can be drawn between the discharge and percentage deviation.